Good afternoon. So we have now arrived at the last session in what has been, I think, a really amazing symposium. So I'd like to introduce myself first of all. I'm Jessica Kogel, and I'm with the National Institute of Occupational Safety and Health. We're part of the CDC, and normally when I introduce myself, I get a lot of kind of confused stares because I'm a mineralogist, and people really don't understand why a mineralogist would be working for the CDC. But I think you'll hear more about that in this session from our two speakers, and actually it's already come up. We hire a lot of geologists and mineralogists. And so this session is Minerals and Industry, Evaluating the Real Impacts of Mineral Dusts on Human Health. And I kind of came up with a subtitle for this session, and I would like to call it When Science, Regulations, and Terminology Collide. So, and you'll understand that, I think, as you listen to the presentations. So, you know, we've talked about a lot of different things during this symposium, and you know, just even today, we've been to Mars, we've been into the deep subsurface, we've been into the body, and we're going to continue in that vein of the body. And we're going to talk about minerals and how minerals interact with the body, particularly in terms of dusts and respirable hazards. So this whole idea of health effects is something that MSA actually, as a field, I think really established. It was, I think, almost exactly 25 years ago. There was I guess it was a workshop that was in Nantucket, and I think some of you participated in that. And there was a proceedings that came out of that, and that's health effects of mineral dusts, and it was George Guthrie and Brooke Mossman that edited that. So at that time, I think the field really became established, and it's a really fascinating one, and I think there's been a lot of advancement in the science in some ways, and then in others, not much has advanced. And a lot of that is around some issues related to terminology and imprecise terminology. So both of our speakers are going to address that issue, and I would like to actually make an offer and maybe even a plea to this community of mineralogists that this is an area that you can really have a huge impact. And so I hope that we can stimulate some interest in it, and we would love to see more mineralogists working in this really vitally important area and getting involved in some of the policy around these big issues. So with that, I would like to introduce our two speakers. Our first speaker will be Anne Wylie. She's from the University of Maryland, and she'll be talking about what makes an amphibole asbestos, history and status of regulatory issues dealing with amphiboles. And then following Anne will be Matt Sanchez. He's with the R.J. Lee Group, and he's going to talk about mineral misidentification in connection to potential hazards of mineral dusts.
Thank you very much to the Society for inviting me. I'm extraordinarily honored to be here with you all, and it's been a marvelous experience overall. So I'm going to talk a little bit about what asbestos is and why that should be a question, and some of the issues in the regulatory sphere, and I'm going to show you some work that I'm doing presently at the end of the talk. Forward. Okay. So we have to begin by asking what asbestos actually is. And I've got three definitions up here. It really depends on your perspective. The commercial term is the one that is associated with things that were mined and used as insulation and all of the areas that asbestos has been important to the society. And the commercial term really deals with its physical properties because that was why it's mined. The regulatory definitions start with the mineral names. And you see I have in brackets there riebeckite next to the word crocidolite. In the regulatory terminology, even though we mineralogists have rejected the terms crocidolite and amosite. They are in the laws, and so they will be in my vocabulary. I apologize to the purists out there. And the initial regulatory definitions just gave the names of the minerals. They didn't have the italics crystallizing in the asbestiform habit. So in regulatory world, we begin with the name of the mineral itself. Then it has to satisfy a certain dimensional criteria in order to be assessed for abundance. The third definition for asbestos is very simple. Any particle that causes asbestos-related diseases. And those diseases are mesothelioma, which almost entirely, not exclusively, there are some spontaneous mesotheliomas, but they're associated with exposure to asbestos. Lung cancer is also associated with exposure, exacerbated terribly by smoking, and the independent effects are hard to separate. And then asbestosis, which is basically scarring of the lung tissue. It's a form of pneumoconiosis that is caused by asbestos. Well, I'm going to begin with the medical definition. So I want to talk a little bit about samples that we know cause disease, so that we don't have all these other issues. We want to look at what actually is it that humans have been exposed to that causes asbestos-related diseases. And I'm going to talk primarily about mesothelioma because it is the hallmark of asbestos exposure. And we have a lot of places where amphiboles, and I'm also going to talk primarily about amphiboles, where amphiboles are known to form in the asbestiform habit and to have caused asbestos-related diseases. So we have a lot of places that we can go to, and we can actually look at these particles and these populations that cause the disease. So this is a zero-level Weisenberg photograph that I think I took 40 years ago, at least. And I was just beginning to think about asbestos. The Bureau of Mines was sponsoring my work. They were very interested in asbestos and what it was and how to identify it and where it occurred and all kinds of reasons. And so I took this picture, and it was the smallest fiber I could possibly isolate. It was a few tenths of a millimeter. I don't know, it was so tiny, and I put it on there, and what did I get? I didn't get a spot pattern. I got a line pattern. And this told me right away that what I had was not a single diffracting lattice, but many, many, many that shared a common axis, but which were randomly oriented in all other directions, the A and B directions. And so that's referred to as the fibrillar growth habit of asbestos. And the photograph of any of the commercial asbestoses, the X-ray photograph like this, would be exactly the same. You really can't tell them apart. So this known carcinogen, asbestos, has a lot of characteristics that make it identifiable. It has anomalous optical properties that arise from the structure. It has a very high tensile strength, which we know is associated with the very small size of these fibrils. There are other reasons that tensile strength occur, but that's a primary variable. The luster, a silky luster, looks like flax. These are terms in mineralogy textbooks. They're flexible and have high aspect ratio. This all results from this fibrillar structure. And so let's look at the width variation across the different types of commercial asbestos, and I've put the two extremes here. Crocidolite from the Cape, South Africa, is shown on the left, and anthophyllite, asbestos from Finland, is on the right. And the crocidolite is the highest quality asbestos. And you can see these are very, very careful measurements by TEM done by Kim Shedd, who's now at the USGS, but it was at the Bureau of Mines at this time. And she showed bimodal fibril widths. She showed that they were extraordinarily tiny. These are around 0.04 and 0.08 microns in size. And there are none here that are less than half a micron in width. Anthophyllite asbestos, on the other hand, is much poorer quality. The tensile strength is much lower, and for all the reasons that we can see would be directly attributable to the fibril width. And one of these is a pointer. So I want to just point, I'm going to talk about two width dimensions, and I want to point them out so that when I talk about them later, you'll remember where they are on these frequencies. And so at 0.15, we are right here for crucidolite. So at 0.15 micrometers, they're almost all smaller. And for anthophyllite, on the other hand, at 0.15, well, there's only a very small amount that's a lot smaller. At 0.25, which is another marker that I'm going to use, it's basically all of crucidolite. And we got, at 0.25, we get a little more. And so, in fact, there's a little mode here in anthophyllite, which I actually think is really the real asbestiform part of this particular sample. Whoops, wrong direction. So let's talk a little bit. My topic was regulatory criteria. And so I want to talk about it in sort of sets. And so before 1992, in about 1971, I think, was the time that OSHA and EPA were both formed. The first regulations for asbestos were written. The United States was way behind the rest of the world in regulating this known and terrible carcinogen. But it's the only carcinogen that I know that is defined by its size and shape. We have these these minerals that make it up, but really it's the size and the shape that is what's counted as asbestos fiber in assessing exposure. The Occupational Safety and Health uses a membrane filter method. You can't tell cat hair from asbestos, but because it's phase contrast microscopy, and so they count anything that's 3 to 1 with length greater than 5 when they're assessing occupational exposure. In 1986, the HERA rules were written for asbestos removal from schools, and a different criteria for fiber was defined, and this was greater than 5 to 1 or greater in aspect ratio, and a length greater than 0.5 micrometers, so you know we had to go to a TEM here. When we look at water, the EPA's regulations were first written in 1983, 3 to 1, length greater than 0.5. In 1994, they decided to only count lengths greater than 10, but the 3 to 1 still holds. So if you're wondering, your thumb is 3 to 1, and your little finger is 5 to 1. So these both qualify. And there's no scale on here, and I didn't put a scale on here for a purpose because there's no scale. These are all aspect ratio defined. As long as we get them larger than 0.5 or 5 micrometers for one, 0.5 for the other, all that matters is the aspect ratio, so who needs to know how big they are? So on the left, this is actinolite cleavage fragments, and you can see they are both thumb-sized and little finger-sized. And on the right, we have tremolite asbestos from Metsovo, Greece, which is a terrible carcinogen, and the population has suffered greatly from asbestos-related diseases. They use this material in the whitewash of their buildings. I don't think they use it anymore. But they both qualified as asbestos. So you can imagine there was a gigantic outcry. So in 1992, OSHA reconsidered. And they held hearings, and they reviewed their criteria and their nomenclature, because at that time, all they had identified is 6 mineral names, and this longer than 5 and 3 to 1. So they looked at all the evidence, and they found that there was no evidence to conclude that cleavage fragments were the same, presented the same magnitude of health effects, and there's no employees wouldn't be any worse off if they changed these regulations, and so they hereby removed the non-asbestiform habits of these 6 minerals from the asbestos standard, and therefore today Post-1992, all the federal statutes specify the asbestiform variety of the minerals that are left. Well, the problem is that they didn't identify asbestiform, and there's a good group of people out there, particularly in the legal system, who say that thumb-shaped particles and little finger-shaped particles are what they meant by asbestiform. So that remains a serious problem, but there is an exception, and that's the EPA method. Was produced in 1993. It was a replacement from an earlier terrible method, and it was a PLM method for bulk materials. And they had criteria that they put into this federal procedure, and their population-based characteristics. So you look at a whole bunch of materials, and you began to assess whether or not the habit of asbestos that I showed you early on, that fibrillar structure, is it there or isn't it there? And these criteria pretty much isolate mineral occurrences to the asbestiform habit. Well, that was all well and good, and then in 2006, NIOSH, and Jessica wasn't working there then, NIOSH put out a roadmap for research on asbestos, and they renamed the problem, and they called them elongated mineral particles. And so what we now have is elongated mineral particles, and that is longer than 5 and 3-to-1 aspect ratio. Although sometimes it's used only to specify aspect ratio. And I sort of thought this was a good idea because the problem that I had with the cleavage fragments, the two pictures that I showed you, is that to me the word fiber meant that it was a particle that attained its shape during its growth, when it formed in nature. So that's what fiber meant to me. And so I was always offended by the idea that a cleavage fragment could be a fiber. And it also was extraordinarily confusing to the lay public. You can just imagine. I mean, they didn't have a clue. So I thought it was a really good idea for a while. And then what happened is that, well, gee, these asbestos fibers are now EMPs. All we have to worry about is elongated mineral particles, and we don't even care what they are. So the taconite, our iron mining district, taconite mining in Minnesota, it's a very complicated story, and I think extraordinarily interesting, but I don't have time to talk about it today. But there's 10,000 people in a cohort who began work, some of which began work in 1948 and have been followed extensively. And up to the year 2000, there was no expression in this very large cohort of any asbestos-related diseases. And then all of a sudden, out of sort of nowhere, there have been more than 100 mesotheliomas in that particular cohort, and it remains a great mystery. So, but at any rate, all of a sudden, people started being interested in EMPs. Here's NIOSH saying EMPs, we need to know something about them. And here's the taconite. So we have a spate of publications that don't identify the minerals. And so they started measuring airborne EMPs. They have done case-controlled studies between mesothelioma and duration and possible EMPs. So we're beginning to try to identify the mesotheliomas with this exposure. And they're not amphiboles, by the way. I mean, there was actually one of the papers said that they didn't find any amphiboles. We know that in the eastern end of the Mesabi, we have lots of grunerite and actinolite, ferroactinolite, but they weren't there. So I think these must be fibrous clays. There's greenolite and minnesotite and stepnomalane and sepiolite, and I don't know what else is on these filters, but neither do they. And pleural abnormalities correlate with EMPs, whatever they are. So we have this whole health study going on. And then, this is in the Congress right now, unless they withdrew it in the last few weeks, but I copied this right off. Senate bill, Ban Asbestos Act of 2019. They've added a couple of minerals to the asbestos mineral list. They do say asbestiform, unfortunately, but they've added, there's amosite, there's crucidolite, but they've added richterite and winchite. And the reason they've done that is because we know that the amphiboles that occur with the vermiculite at Libby, Montana have resulted in mesothelioma among the workers in that vermiculite industry. But they also added the non-asbestiform varieties of richterite and winchite. And so there we are. I don't know what's going to happen to that. I know the industry is going to try to oppose it, but there it is. So all of these issues out there that relate to regulatory, we can deride and we can say they don't know what they're talking about or whatever. But the real problem is that it obfuscates what's actually going on. So all the particles that meet these broad dimensional criteria are considered to be equally hazardous. And we know that is simply not true. So this paper was published in 2018, but the work has been, it's a summary paper, and it's for other work that's been in the literature. So for at least the last 10 years or so, we've been able to produce a measure of mesothelioma potency among people who were exposed to only one mineral product or one mineral occurrence. And these are the crocidolites from the Cape Province and from Australia, amosite from Transvaal, the winchite and richterite asbestos from Libby, and the overall chrysotile. And they also, the Home State Gold Mine is a quartz grunerite rock in which the gold is found, and that was mined for a very long time, and there's no excess disease been reported there. So we do have a whole set, and they're normalized for exposure. And so what this tells us is that the occurrences here at the same exposure as it's measured, and that's a whole other story, but as the way the exposure is measured, there's a great deal of difference in the potency of these minerals to cause mesothelioma. And you can see crocidolite is the highest. Whoops. Sorry about that. I'm really kind of inept here. Crocidolite is the highest at 0.588, and these are, why they use all these decimal places, I don't know, but they do. And then we have the confidence intervals given there. And crocidolite is 2 orders of magnitude greater than chrysotile. Now, it's a different mineral, chrysotile, and we know chrysotile is fairly soluble, so there's a mineralogical property that's behind that. But the rest of these are all amphiboles, and while there are some small differences in solubility, I don't think they really have any relevance in the biological systems here. So what's going on? What is it that we have happening here that we can talk about? Well, I'd first like to just, before I look at the next few slides very quickly, I'd like to just recognize my people that I am working with. The field that I operate in and the other people here has a lot of different people in it, from the health sides, from risk analysis, and Andre is an expert in risk analysis. Alan operates the TEM, and Andrew is an industrial hygiene. So I just want to be sure to recognize them. So we frame our thinking about how to think about mesothelioma and minerals and how to understand that array of potency by kind of a very generalized equation, which says that the potency factor has a bunch of regression coefficients, but it has a dimensional parameter, and it probably has a coefficient dependent on mineral characteristics. And certainly, I think there's probably several, maybe many here, but one is certainly the mineral structure, because we know for chrysotile that it's soluble in the human body, and the residency time for a chrysotile fiber is less than a year, so they disappear, but the amphiboles don't. And so we know there's something there for chrysotile. But the rest of the variables in the mineralogy that affect these health effects remain unknown. So the dimension, I'm sorry, let me just go back quickly. So the dimensional parameter is what I'm going to talk to you about just a little bit today. I'm going to assume we're going to work only with amphiboles, and I'm going to put aside chemical variability for at least a first pass through. All right, so the dimensional criteria that I'm going to just graph for you and correlate with mesothelioma potential is the width of the fibers. And it's just a very simple parameter. And I've got two variables, one width and 0.15, which I showed you, that includes basically all of the aerosolized crocidolite, and one less than 0.25, which I didn't show you what amosite looked like and all these others, but it incorporates them as well. So I have the proportion of particles that are longer than 5 micrometers that reflect the occurrences in these 4 locations. Now these data, I should have another slide for the sources and references for all of these data, because these are sets of data, many sets of data in each one of these. So I have the standard deviations are shown, and they're actually, with respect to the size of the percentages of particles that fall in these categories, pretty small. And what happens is that dimensional characteristics of an occurrence are retained in the aerosol. And some of these were bulk samples, some of them were air samples, they were done by different labs, they were done over different protocols, and yet the mineralogy controls the nature of the aerosol, and it's a very, very important thing to keep in mind. So I've correlated it, simple, with the potency for mesothelioma, and which we have on the y-axis, and this first, figure out which one of these is the pointer. There. The first one, this is 0.15, and we're using a power function, but you can see that the exponent here is very close to 1, so it's almost a straight line. And our correlation coefficient's very high. Now we only have 4 points. I know, we only have 4 points. But those are the only data that we have. We didn't force it through 0. We could have used Homestake and put 0, 0 down there. But I didn't do it because Homestake is not asbestos, and I just didn't want to put that on the slide. Whoops. Sorry, I'm such a, no, I'm going the wrong way. I am really bad. All right, maybe I can get that next slide back. I need to do that. That last slide, I absolutely have to get back. No, third slide from the end. Okay, so these correlations are very high. The correlation coefficients are extraordinarily high. But the question is, can we use this to predict anything? Can we utilize this to get away from that longer than 5 and 3 to 1 and begin to make some statements about within that population where exactly are the carcinogenic fiber? Okay, so the next slide. I only go one. Yes. So these are the predicted values. And I have listed the crocidolite, the amosite, and the winchite asbestos on the top, and in parentheses, those are the values that come from the epidemiological studies in those locations. And then our values that we predict we've derived them, and now we're going to predict them. That's a neat trick. But I wanted just to show you how close it was. These are the 2 models and how they compare in terms of reproducing what we know. And then I've taken tremolite asbestos from Greece, this little town in Metsovo where the mesotheliomas are very rampant, anthophyllite asbestos from Russia, anthophyllite asbestos from Finland, and asbestiform fluoroedenite from Biancavilla, Italy, and I'm very grateful to the authors who put their, Paoletti and Bruni, they put their data in the literature. So we were talking about that somewhere so that I could actually extract it and utilize it in this modeling. I put down here at the end a fibrous glaucophane. The Calaveras Dam project in California had to excavate huge quantities of riebeckite bearing rock. And glaucophane bearing rock is blue, and they treated it like it was asbestos, but in a way, even though it isn't, but it was fibrous. And these are data that reflect the proportions of these 2 different parameters, the 0.15 and the 0.25 for fibrous glaucophane. So we're looking for a tool to try to help predict when construction projects go on, they're building a road in Nevada or excavating a dam or whatever it is, and we're uncovering amphiboles and there's fiber in there. How do we know whether or not we have a hazard and what kind of precautions we should take? And so that's sort of the goal of the work. And I'd just like to end by telling you that this is a fascinating field, and there are so many things that we don't know. It is just unbelievable what we don't know. And really, it's because the medical community thinks that minerals are chemicals. And they have absolutely no idea of the complexity of particulate matter, just none whatsoever. And I was told by a US senator about 10 years ago that I should stop talking about anything medical, because how could I possibly know? But it's perfectly okay for the medical people to talk about minerals, because, you know, we're just pawns of the mining industry or something. So to understand the disease patterns, I believe we absolutely must understand the minerals. We have to start at the exposure. It is not just a bunch of dust. And there are these questions that linger. Is aragonite, some people think that aragonite is the most carcinogenic substance we know, mineral-wise. Is it independent of size and shape, or is it only the woolly aragonite that has fibril diameter of about 0.03 micrometers that he was using that made it so carcinogenic? But for the outside world, it's the mineral aragonite. And how about the composition of amphibole? There's a lot of discussion about the role of iron in redox reactions that take place on the surface, whether that induces inflammation, which is a precursor for malignancy. So there's a lot of interest there, and we don't know anything about that. Do you think that the mineral talc can actually cause ovarian cancer? That's in the courts right now. There's tens of thousands of cases claiming it. And how about the size of particles that can move through your body? You know, when you inhale mineral particles, some of them can just go everywhere. And they have crossed the placenta into a newborn baby. And so what is it? What are these parameters that control the migration of particles in our body? What sizes and what are they? And we need to know that. And where do they go? There's a good question. And quartz, why is quartz biologically active? Not all the surfaces are the same. There are young men dying of silicosis in the coal mining industry from exposure to quartz. And it is a terrible disease, and we don't know why. Why is quartz so biologically active? And it continues to be active after you stop inhaling it. So I hope maybe some of you will think about some of these problems, take them back to your communities, and engage yourselves, if you can, in these discussions, because the lack of, we have some mineralogists. I mean, I'm sure you've heard Mickey talk about all these things, and we're a small number, Julie Pierre is here, of a sort of defended people, trying to just bring some sense to this issue. So thank you very much.